This podcast is brought to you by LMU Munich.
Okay, thank you. All right, so today I will explain, the joint work with Ali Shamseddin and Slava Mukhanov. And so what we have found, if you want, is a way to, quantize the geometry in the following sense. In the sense that, as I explained in my second lecture yesterday, the line element, the fact that the line element has topological content, and that this topological content was representing the fundamental class in KO homology, that was sort of quantizing, if you want, the homology side. Now, to quantize the cohomology side, this means that one will find a K-theory class which will be dual to this one and which will pair by the index pairing. And in order to understand, if you want, the motivation behind it, I will make concrete computations on the blackboard for a little while. But if you want, what was around for a long time as an analog of P, when you write down the Heisenberg commutation relation, you write P commutator Q is equal to IH bar. Okay, and what was around for a long time was the fact that the Dirac operator, if you want, assembles all components of the momentum into a single entity. And so, it was not so difficult to find the analog of P in this dictionary. But what took us a lot more work was to find the analog of Q. Now, if you want, the philosophy is the following. The philosophy is that when people tried to generalize the Heisenberg commutation relations, they went into a representation theory. So they thought about it as a representation of the Heisenberg group, which is a Lie group, and then they generalized these representations to more general Lie groups. Like, for instance, you have the Wigner idea that particles are irreducible representations of the Poincaré group, and so on and so forth. But somehow, it is very clear that if you stick to Lie groups, you will never get representations parametrized by geometries. And however, what I will explain is that in what we do, we shall get irreducible representations parametrized by geometries. And these geometries will be four-dimensional geometries. They will be spin geometries, arbitrary except for the fact that they are compact spin and that the volume is quantized. Okay, so this will be the outcome. So, so one has to reflect about it in the sense that it will not be the representation of a Lie group, okay, but it will be the representation of a commutation relation. So if you want, it will be a representation of an algebra. And it will not be a representation of a Lie algebra. Okay, so that's the difference. All right. Okay, so this is the framework. Now, in order to understand, so as I said, it was difficult to find the analog of the position variable, but it came out in the end to be incredibly simple, because the idea was, again, to assemble the various coordinates into a single entity and using Clifford algebra. So if you want, the idea was exactly the counterpart of the idea which was used for the momentum, but applied now to the coordinates. All right, so this is what will happen. And in order really to understand what is going on, I want to give you two examples. One which I will leave you as an exercise, and the other one I will do some computation on the blackboard to make it plausible. So the one that I will leave you as an exercise is the following. You know that the circle has only one geometry if you give its length. There is no 1,000 ways because there is no curvature or anything like that. And of course, this should be compatible with our point of view, and I claim it is. So I claim that if you take all the rules of noncommutative geometry, you'll find the circle by looking at representations of the relation which is written there. So of this relation here, which is that you take a unitary operator. So the only condition on this operator is that u star u is equal to u star n is equal to 1. Okay, so that's the rule. And the other rule is that, of course, the operator D is self-adjoint and so on, as in spectral triples, but you have the rule that U star D commutator U is equal to 1, yes. Now, if you look for an irreducible representation of these relations, what you find out very quickly is that you can rewrite this as U star D U minus D is equal to 1, so is equal to D plus 1. So what does it mean? It means that the spectrum of D has to be invariant under a shift of 1 or of minus 1. So the spectrum of D has to be up to an overall shift, the integers. And it cannot be more than once the integers, because otherwise it wouldn't be irreducible. So once you know that your Hilbert space, you can think it as being L2 of Z. And you can think of D as being the diagonal operator in this L2 of Z. And then you find out what is the operator U in this basis. And you find out that because U is shifting the spectrum by 1, it's just the shift operator. And so you have a unique up to a choice of a scalar, which is unimportant for this, and which would be fixed if you have the J. What you find out is that this geometry is unique. You can compute the spectrum of U. The spectrum of U will give you a circle. And you can compute the distance between 2 points of the circle by using the formula which I was showing on the first day. And what you will find out is that you get the ordinary metric on the circle, but of length 2 pi. So the volume is quantized, if you want. So it's quantized by this condition. Okay, so this is a very, very simple example. And of course, it has an analogy with the Heisenberg commutation relations in the sense that you could think of this as a kind of a partly discrete Heisenberg group. Okay. Now, so this is for this example. But now let us see an example which is even more intriguing. What is more intriguing about the second thing, about the two spheres, if you want, is that you start with two things which are completely discrete. I mean, you start with M2 of C. So M2 of C, I remind you that there are elements of 2 by 2 matrices which are canonically denoted by Eij. So, I mean, for instance, E12 is a matrix which is 0, 1, 0, 0. Okay. So you have these canonical elements. And then what happens is that if you have any algebra which contains M2 of C, so an algebra with unit which contains M2 of C, so if I have M2 of C which is contained in some algebra A, whatever this algebra A is, okay, I want an evolutive algebra and so on, then it turns out, it's a very simple fact, but which I want to explain on the blackboard, that any element of A can be written as follows. So then any element of A, for any x belonging to A, you can write x in the form x equals E11 times A11 plus E12 times A12 plus E21 times A21 plus E22 times A22, where all these elements, Aij, they belong to the commutant of the 2 by 2 matrices. Okay, so they all belong to the commutant of 2 by 2 matrices. Okay, so how do you do that? It's important to understand a little bit these computations. So how do you do that? You see, when you have the element x, how do you go to the commutant? Well, you can go to the commutant as follows. I mean, if I have an element x, okay, of course, for instance, I should consider, if I want to get A11, I should consider E11 x E11. Okay, but this element E11 x E11, it's not in the commutant. It's sort of squeezed between two projections which correspond to E11. So how do you make it into the commutant? You make it into the commutant by adding plus E21 x E12. Okay, then I claim it's an exercise. So it's an exercise to prove that if I call this element A11, okay, yes, if I call it A11, then I claim that you have the following two things. First of all, you have that A11 commutes with M2 of C. Okay, I mean, you can see, for instance, that A11 commutes with E11, because if I put E11 on the left, I will get this one. If I put it on the right, I will get this one in the same way. It's a little bit more tricky to see why it commutes with E21, for instance, but you can do it. Okay, and moreover, it satisfies that E11 x E11 is equal to E11 times A11. That's again completely easy. Okay, and once you know that, then you can prove easily this formula. Okay, so this you should know in general. It's a completely general fact that whenever an algebra contains M2 of C, okay, you can write any elements as a matrix. All right. So now what happens is, how can it be that we get the functions on the two spheres by just taking M2 of C and the projection? Okay, I mean, this is sort of very strange, you know. So I am adding to M2 of C an element which is self-adjoint and whose square is equal to itself. I call it little e. Okay, and moreover, I will assume the following. Okay, so I am adding to M2 of C. Okay, an element which the only relation that I will assume for this e is that when I consider its trace, so if you want, if I consider the sum of the diagonal elements A11 and A22 is equal to 1. So the trace should be equal to 1 for this e, okay? And this trace I do not like this. Okay, so how can it be that we generate functions on the two spheres? I mean, this is a little calculation which I want to do, otherwise it would not be understandable, but I will explain later. So what do? Well, I write my element E as a 2 by 2 matrix. I am allowed to write it as a 2 by 2 matrix whose entries are in the commutant, okay, just because of what I explained before. So I write it as a 2 by 2 matrix whose entries are in the commutant. Now, this 2 by 2 matrix will be of the following form. Because the trace is equal to 1, here I will have some element T, which will be self-adjoint, because E is self-adjoint, okay? And here I will have 1 minus T. This is because the trace is equal to 1, okay? Now, outside the diagonal, I will have some element Z, and here I will have Z star, because E is self-adjoint, okay? So what do I have? I have two operators, two elements, if you want, T and Z. And Z, I have its adjoint, okay? Now, of course, in general, I mean, I would be unable to say anything, because there is no reason that they commute or anything like that. But let me show you why they commute. So now I will compute the square of E. And I mean, my assumption is that the square of E is equal to E itself, okay? So let's compute the square of E, okay? How do we compute when we have matrices? Well, we compute line by column. So I repeat my matrix here, okay? And I compute line per column, okay? So what do I get? What do I get as an element in the square? So when I compute E square, okay, I will first get something up here. What will it be? It will be this line per this column. So it will be T square plus Z star. Okay? Okay, and so, okay, so the first equation, and this has to be equal to E, so it has to be equal to T, 1 minus T, Z, and Z star. Okay? All right, so my first equation I get is that T square plus Z star has to be equal to T. Okay, that's fine. All right, so now what do I get when I compute this element here? Well, I get this line multiplied by this column. Okay, so what is it? It's a TZ, okay, plus Z times 1 minus T, plus Z times 1 minus T. What does it tell me? It tells me that TZ plus Z times 1 minus T is equal to Z. So it tells me that T and Z commute. TZ is equal to ZT. Okay, they commute. That's a good sign. All right. And then what is going on? Let's compute now the element which is down here. All right. Okay, what does it give me? It gives me this line multiplied by this column. So now what do I have? I have Z star Z, not Z star. So this is good. Z star Z plus 1 minus T square. Okay, and it should be equal to 1 minus T. Okay, but what is that saying? This is saying that Z star Z, okay, plus, let's compute this square. There is a 1. It will cancel off this 1. there is a minus 2t. Minus 2t, with this, I will put it on the other side. With this minus t, it will give me a t on the other side. Okay, so this will tell me that when I equate that, I will have z star z, okay, plus t square, okay, is equal to t. Okay, but z star z plus t square is equal to t is almost the same thing as over there. And what do we conclude from that? We conclude that z is a normal operator. It satisfies z star z is equal to z star. A normal operator is the same thing as two commuting real operators, okay? And at the end of the day, we have three real variables. We have the two components of z and the t. And what do they satisfy as an equation? They satisfy this equation. That's the equation of the two sphere in 3 space. Okay. Why is it the equation of the two sphere? Well, just make a trivial change of variable in t, take t minus 1/2 as a new variable, and you will get the sphere you'll get the sum of 3 square, which is equal to 1/4. Okay. Okay, so you see what happens. I mean, it's a very, very strange thing. It's a very strange thing because, after all, what we have done, we have started with 2x2 matrices plus a stupid variable, a projection, a variable that takes only 2 values. But because they don't commute, they generate a continuum, which is a 2-dimensional sphere. Okay? And a long time ago, around 2000, I had noticed that then you can actually get all the metrics which have the fixed volume element on the two sphere by writing another equation that actually resembles the equation for the circle and which connects the Dirac operator on the two sphere with the projection E. Okay, and at the time, okay, I mean it was very limited. It was limited to dimension 2. So on the forth, okay, then we extended it to dimension 4 with Gianni Landi and then with Michel de Bois-Violette. But, okay, I mean, we had not really understood the reason which is behind this computation. And the reason which is behind this computation is, in fact, the Clifford algebra. Okay, and this is what we shall understand today. Okay. Okay, so now let me go through the slides. And so, I mean, our point of departure are these examples. These are the motivating examples. But, okay, so what do we do? In general, if you want, what we want to do is to extend these conditions. So to extend this condition, we consider, if you want, the Feynman slash now, not matrices like this, but the Feynman slash. So we take gamma matrices, and our y, which is pretty much 2e minus 1 in this language, okay, is now an element in, I mean, with if you want, components in the Clifford algebra. So it's equal to ya gamma a, but let's take kappa equals 1 to simplify. When you write y square equals 1, okay, what you find out is exactly as here you had the commutation of the components. Here you'll find that these components ya have to commute with each other. Why do they have to commute with each other? Because otherwise there would be cross terms in the square. If they wouldn't commute, you would have terms like a ya, yb commutator times gamma a, gamma b, and so the square couldn't be equal to 1. Okay. So the fact that but this example is pretty illustrative. It showed you how it happens. You know that the components commute. So the components have to commute, and moreover, if you want, what happens, of course, is that when you look at the Clifford algebra, I mean, if you complexify, it generates a matrix algebra of dimension 2 to the power n over 2, and so I mean, you are pretty much in this situation where you are looking at the matrix algebra. And in particular, you have a notion of trace, so you have the projection on the commutant of the Clifford algebra. And then our starting point with Ali and Slava was to write down an analog of what was giving, if you want, the matrix in the case of the two sphere. Namely, we wrote down this Eier-Heisenberg condition. This is what we call the one-sided Eier analog of the Heisenberg relations, because as we shall see very shortly, this would give you only spheres. And I will explain the proof why it only gives you spheres. Okay? But of course, we want to have general manifolds. And what we shall see is that when you take the two-sided equation, then you get general manifolds. But we started with one-sided. Okay, so what is this equation? Sorry, what is this equation for the Dirac operator? And why is it an higher form of the Heisenberg commutation relation? Well, you take the commutator of the Dirac operator with y. Why do you do that? Well, you do that exactly for this reason here. You see, here I was taking one commutator, but I was in dimension 1. Now, if you are in dimension n, what you take the commutator with y, but you multiply it n times by itself. Okay? So it takes this operator. What are the brackets on the two sides? They are what I used here already when I said that the trace of E is equal to 1. So they are the trace, if you want, the projection on the commutant. Okay, and the condition is that when you take this trace, what you get is the gamma. What is gamma is a chirality operator, and here we are working in even dimension. So there is a chirality operator, and if kappa is 1, of course, square root of kappa, I take it to be 1. Okay, so gamma is a chirality operator. In the case of an odd space, like the case of the circle, you would replace the kappa by the gamma by 1. Okay, but of course, it's quite important in the even case to use gamma. Okay. And as I said, I mean, this notation with the brackets on the two sides, it means if you want the projection on the commutant or the normalized trace, which is the same thing. All right. So this is our basic equation. Now it's a basic equation in even dimension n, okay, and we want to understand what it does. Okay, what are, if you want, the irreducible representations of this relation. Okay, and the first thing to observe, which will be absolutely crucial in general, is that this relation implies a quantization of the volume. I mean, I will explain why in general, but we shall see why in the concrete calculation. But why is that true in general? It's true in general because of what I said yesterday. I explained yesterday that the Dirac operator gives you the fundamental class in K-homology. So, but the K-homology is an integral theory. It's a theory with integral coefficients. So, in particular, you have the index theorem, which tells you that when you pair an element of K-homology with an element of K-theory, you get an index, which is an integer. Okay? And it turns out that when you compute the index formula, I will explain that later in the greater generality, you will find that the index formula in that situation simplifies enormously and just gives you the volume. So there are no lower chain classes, and what you get is simply the integral of the volume of the space. And because it's an index, this volume becomes quantized. So it has to be an integer. Okay? So it has to be an integer. And that's a very fundamental principle. So this is a general principle rather than, I don't want to introduce it at this moment as a theorem, but it's the pairing of the K-homology class with the K-theory class, and it gives you exactly an integer. Okay. So our first result with Ali and Slava was at first disappointing, if you want, because okay, when you write this equation, you hope to get arbitrary spaces and so on, but you don't. And what you find out is that if you take the spectral triple associated to a spin Riemannian manifold, and you try to solve this equation for such a spectral triple, you find out that it's possible if and only if this manifold breaks as a disjoint union of spheres of unit volume. And on each of these irreducible components, you can fix the Riemannian metric arbitrarily, except that it should have unit volume for each component. So the picture which emerges, if you want, is this one. Okay? It's little bubbles, if you want. Of course, this unit volume means Planck volume when you think about physics. So, I mean, this would mean, you know, a union of very, very tiny little spaces. Of course, it's not realistic. And how do we, I mean, it's quite important to understand how this proof goes. Okay, so as I explained yesterday, I recall that the Dirac operator is given using a Verbine. Okay, it's given by this expression, gamma mu square is -1 here. Okay, d by dx mu plus spin connection. And so how do we compute? How do we compute this this quantity here? Okay. How do we compute this quantity? Well, the computation is the following. So you see, when you, so the y's are expressed in terms of the gammas, and they commute with the gammas. So when you compute the traces, the only traces that you will have to compute are the traces of a product of many gammas, but exactly n plus 1 of them, because in the formula there were n plus 1 apparitions of the term y. Okay, there was y in front, and then there was the commutator y to the power n. So it appears n plus 1 times. So what you have is n plus 1 occurrences of the gammas, and when you compute the trace of n plus 1 product of gammas, what you find out is you find out the totally antisymmetric tensor, epsilon A, B, and so on. Okay, so that's what you get for the trace part. And then you compute for the rest. You compute when you compute the commutator of D with the Y. Okay, the gamma spit out, and what you have is the partial derivatives of the YA, which appear. Okay, but they are assembled together by the spin matrices. And of course, this gives you what? It gives you the Clifford multiplication by the gradient of the YAs. So when you compute this commutator, it's just given by a sum of the gradient of the YA times the gamma matrices, okay, which is very simple. And so when you compute the expectation of this product, what you have is you have the totally antisymmetric tensor multiplied by the product of the gradients and with the YA in front and some power of I at the beginning. Okay, so that's what you have. That's what you have for this expression we are computing. And now what happens is that there is a nice generalization of the commutator of two operators, which is a multiple commutator. So if you take any operators, in fact in an algebra, the multiple commutator is defined as a determinant, if you want. So what you do, you take all the possible arrangements of the product, but you put in front the signature of the permutation. And what is important about this multiple commutator is that if you take a linear combination of the original operators and you compute, you'll find that what is in between is a determinant. Okay, so I mean, if you recombine the operators, it will be just multiplied by the determinant. Okay, so if you apply this rule, what you find out is that when you compute this product here, you find the multiple commutator of, because you have the totally antisymmetric tensor here, you find the multiple commutator of the gradients, okay, with the YA omitted. Okay, and then when you compute this multiple commutator, moreover, what you find is that you have the partial derivatives of the y's, and then you have the multiple commutator of the spin matrices, just by multilinearity. Okay, and finally, the multiple commutator of the gamma matrices gives you the gamma 5 matrix, namely the chirality operator, up to a sign. Okay, because if you take them in the right order, they will give you exactly the chirality operator. So at the end of the day, what do you find out? You find out that this expression that you want to compare with gamma, okay, is equal to gamma, indeed, but multiplied by a factorial, this is an important, multiplied by the determinant of the Vierbein, and multiplied by omega. And what is this form? Omega is a differential form. Or what is this? What is this omega? Omega is such that, if you multiply it by the dx1 wedge dxn, which is, the stupid volume form, but without the square root. Okay, this product of omega by this dx1 wedge dxn is exactly the pullback of the invariant volume form on the sphere. So on the sphere, if you want, the sphere was defined by the sum of the square to be 1. There is on the sphere the volume form, which is the standard volume form, which is given by this formula. And what you find out is that you have this equality here, where this omega is a coefficient of dx1 dxn in the pullback of the volume form. So putting everything together, after doing this computation, putting everything together, what do you get? You get that the one-sided equation that we had, you use the inverse Vierbein, it's exactly equivalent to telling that the volume form, okay, the signed volume form of the Riemannian manifold is equal to the pullback by the map Y of the volume form of the sphere. So that's what you end up with, okay? You end up with the fact that the Riemannian volume form with the orientation is in fact the pullback of the volume form of the sphere, okay? But then, okay, then you are in trouble as soon as n is bigger than 1, of course, because the sphere is simply connected. And if you have an equality like this, you know very well that the volume form of the Riemannian manifold doesn't vanish anywhere. So this means that the pullback of the volume form of the sphere doesn't vanish anywhere. So it means that the Jacobian of the map Y as a map from the manifold to the sphere is never zero. If the Jacobian is never zero, this means that you have a covering, okay? But the sphere is simply connected. So if you have a covering of the sphere which is simply connected, necessarily your manifold breaks as a disjoint union of spheres. I mean, there is no other way, okay? Because the sphere is simply connected, okay? So that's what you get. That's how you prove the theorem. So as I say here, since the sphere Sn is simply connected, this implies that each connected component is in fact a covering of the sphere. And okay, and then I mean, it's not so difficult to prove that you can get any Riemannian metric with a given volume form on each of the components. I mean, this we knew already in 2000. Okay, all right. So I mean, of course, when you reach this point, when we reach this point, I found it quite bothering because what it would tell is that essentially the situation would be that you would only access to space-times which are disjoint unions of spheres. But of course, this is totally unrealistic. And it took some time, really, to get the idea that actually these spheres are a little bit like little bubbles. When you are a kid, you play with little bubbles. And we know that these little bubbles can actually coalesce together and form something, a bubble which is much, much bigger. And so, I mean, after a while, we got this idea that, in fact, there should be two kinds of quanta. Remember that the kappa, which I was using, was equal to 1, but it can have also the value -1. And then we had the idea that we could use both of them, but how did this idea come up? It came up because, in fact, we were not taking advantage of the full structure of noncommutative geometry because we were not using the antilinear conjugation operator J. We were not using the charge conjugation. We were not using the operator that was really essential in order to get KO homology. Okay? And as we shall see, when we use these operators, then everything will be fine. Okay? So, so the idea came up then, if you want, of using the index pairing in a much more subtle manner, which is in fact what I was explaining when I was explaining KO homology, because I was explaining that the index pairing, because you have an action of the algebra and of its commutant, you can actually pair with an element of the tensor product of the two. And so this means that you can use the projection E, but you can do the pairing with, with this element here. You can do the pairing with E times G inverse, where J sends to the commutant. And so what do? You take E to be the spectral projection of this Y, which has a Y plus and a Y minus. And so if you want this Y plus and Y minus, they will now belong to two Clifford algebras, one C plus corresponding to kappa equals 1, and one C minus corresponding to kappa equals -1. Okay, so I will explain in more detail, but then we started so if you want, this will completely resolve the problem. It will allow to get arbitrary spin manifolds of dimension 4, but somehow the motivation behind this was entirely geometric. Okay, so the motivation, if you want, what it means, this Y plus and Y minus, there is a much better way. There is no need to put on the light, but this Y plus and Y minus, what are they? I mean, Y plus square is equal to 1, and Y minus square is equal to -1. So in fact, one should assemble them together. I mean, this is the right way to think about it, namely to think of Y, which is equal to Y plus plus Y minus. Okay, and now instead of having Y square equals 1, what you have is that Y to the power 4 is equal to 1. So I mean, the nuance with respect to what was done before is that it's not the square which is equal to 1, it's the fourth power which is equal to 1. And this fourth power really gives you Y plus and Y minus in a unique manner. So this is the right way to think about it. Okay, this is the right way to think about it. But then so our motivation, as I said, was entirely geometrical. Okay, this was the motivation. But then, okay, we said this should apply in dimension 4 now, and in dimension 4, as I said, we have n plus 1 gamma matrices. these gamma A's. So we have this gamma A. Where should I write? Here. Let me do it like this. You see, we have these gamma A's. Okay, we have this gamma A. Perhaps I put gamma A here. Okay, and we have 5 of them. 5. And the first condition will be, if you want, that gamma A squared is equal to 1. Okay, and so there are 5 of them. Okay, and so this means the Clifford algebra, Cliff, of plus, 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 plus. Okay, that's the first one. Okay, and there will be a second one. So this will be our C plus, if you want. Okay. Okay. Now there will be a second one, which is again gamma A, 5 of them. Okay, and they will satisfy gamma A squared is equal to -1. Okay, and there will be 5 of them. So it will be C minus, and it will be Cliff. Okay, of minus, 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 minus. Okay, and in each case, we are looking for an irreducible representation of this Clifford algebra. In each case. Okay, so we looked at some table. We looked at some table. What did we find? We found that this Cliff plus, 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 it's what? It's M2 of quaternions, direct sum M2 of quaternions. Okay, so when you look at irreducible representation, you can throw away this one. You have M2 of H. The real dimension is, so it's M2, H is dimension 4 real. I have 4 of them, so it's dimension 16. Okay, and total 32. Then look at C minus, you look at the table, what do you find? You find M4 of C. Okay. And irreducible representation, you cannot make it smaller than that. But you see, you have 2 irreducible representations because you have one which is C linear and one which is C antilinear. That corresponds to the fact that you have 2 here. What is real dimension here? 32. And now, okay, we were absolutely amazed. Why? Because these were exactly the constituents that we got when we were looking for the standard model with Ali for totally different reasons. Okay, so that meant that the geometric motivation, which came from 4 dimensions, nothing else, okay, was actually yielding exactly the same algebras. Why exactly the same algebras? Because remember that the y's were YA gamma A. So we were talking, when we were talking about the y was a sum of YA gamma A. Okay? Now, when you take the irreducible representation like M2 of H and so on, you get exactly functions with values in M2 of H. Okay? Or functions with values in M4 of C. Okay? And with Ali, we had been, when we had got these 2 algebras, we had an impossible time to explain to people that they were natural because this one was 16-dimensional real, this one was 32-dimensional real. How do you explain that you choose your algebras to have different real dimensions? Okay? But here, the understanding is completely obvious. It's just because one of the Clifford algebras has irreducible representation of smaller real dimension than the other, because it's quaternions. The other has also 2 irreducible representations, but they have the same dimension. They are both injective. You have no kernel for them. Okay? So, okay, I mean, I don't know, you know, there might be a devil who is putting this to make us go in the wrong direction. But I found this absolutely startling, if you want, the fact that from a totally different reason, in fact, in the work with Slava and Ali, we didn't want to think about the standard model. Our motivation was geometric. We wanted to explain, if you want, the fact that you get a 4-dimensional geometry from these discrete variables in the simplest possible manner. That was it. Okay? So what is going on now? What is going on now is that, okay, so you write this Eier-Heisenberg relation. So it's the same as before, except that you use the Z instead of using the Y. And the Z is a combination, if you want, of the two Y's, so which is a subtle combination which is motivated by K-theory. So you write this relation, and what do you find? There is a difficult lemma to prove, which is that when you take the expectation, so the expectation now is on the commutant of these two Clifford algebras, that when you take the expectation of Z, here Y and Y prime are shortened for Y plus and Y minus, you get the sum of the expectation of the two things. You see, this is not at all obvious because Z is like a quadratic expression in Y prime. It's a little bit like Y times Y prime. So there is no reason why when you compute this with the fourth power, you get the sum of these two things. But okay, this is a lemma. This is a lemma, which is a lot of technical things. And then what do we have now? Now you see, instead of having one map to the sphere, as we had for the one-sided equation, now we have two maps to the sphere. So you have the maps Y plus and Y minus. So we have this our space M, okay, and we have two maps to the sphere. And I mean, the condition which was before, namely the condition, if you want, that the determinant of the Vierbein was equal to the pullback of the volume form, is now replaced by the fact that it is the sum of the pullback by Y plus with the pullback by Y minus. So now, if you want, there is no longer this obstruction that the Jacobian should not vanish. The only condition is that the sum of the two should not vanish. Okay. And why is it sufficient that the sum of the two doesn't vanish? Well, there is a beautiful theorem in differential geometry which tells you that if you take a top degree differential form which does not vanish, then it is a volume form. Okay, so if it doesn't vanish anywhere, I mean, it shouldn't have any zero, then it's a volume form. And so there is a theorem which tells you that two volume forms, moreover, with the same volume are diffeomorphic. So you don't have to worry, if you want, of what type of volume form you get. You just need to get a volume form which doesn't vanish. And then you can use a diffeomorphism, compose the maps with a diffeomorphism to get the volume form you were starting with. All right. So then there is the following result. Our first result is the following, is that, first of all, the same result about the quantization holds. Namely, in any representation of the two-sided equation, the volume, when I talk about the volume, I refer to the leading term in the Weil asymptotic formula. So I refer to my first talk in which I was explaining, the fact that the eigenvalues have a growth. Now, the parameter in the growth of the eigenvalue gives you the volume. And this volume, which is expressed as a Dix matrix, is actually quantized. So this is a completely general fact, okay, that it's quantized. And the proof that it is quantized comes from the lemma, comes from the fact that it's the sum of two terms which are themselves quantized. Okay, so the volume is quantized. But then what we found, the second fact that we found, is that if you take a compact-oriented spin manifold, then a solution of the two-sided equation exists if and only if the volume is quantized, but now it will be just an implicit thing, because it has to be quantized to belong to an invariant which has to be computed. And what is this invariant? This invariant can be defined completely independently of the rest of the talk, okay? And it's defined like this. So you take a manifold M. Okay, so let me show you how it is computed. But okay, so you take a manifold M of dimension 4, oriented, okay, and you take the set of pairs of smooth maps to the sphere. So I put it in dimension n here, okay. So you take this a pair of smooth maps to the sphere from M to Sn, okay. And what you are asking is the following: that when you pull back the standard volume form on the sphere by phi plus, and you pull it back by phi minus, the sum of the two does not vanish anywhere, okay? So you see, I would be in trouble if I had only one map, because then the map would have to have a Jacobian which doesn't vanish anywhere. But now I have two maps, okay? So now I am asking that I have two maps, okay, and that the sum of the pullback of the volume form doesn't vanish anywhere. And what is the invariant? The invariant is the sum of the degrees of these two maps. Okay, so these maps have a degree, okay, and I take the sum of the degrees, and I vary, of course, on all possible pairs. Okay, and now I am asking what is this invariant. So if you want this invariant, it's like the possible values of the quantized volume of the manifold M. All right, and now it's a problem in differential geometry. So now, once you have this question, you can, write an email to your friends who are geometers and ask them, can you help me with this question? Which is what we did, of course. And for instance, I got some help from Simon Donaldson. And so the issue was to determine what is going on. Okay. Now, it's very easy. For that, we didn't need any help. In dimension 2 and 3, it's very easy. Okay, and I will explain why. So let me explain why it is quite easy in dimension 2 and 3 to determine this invariant and to show that it always works. So you see, maybe I should erase this. I don't know. I hope it erases well. Yeah, it erases well. Okay. So why is it easy in dimension 2 and 3? So let's take the case of dimension 2, for instance. Okay, so I take a manifold, all right, and I take the two spheres. So this is S2. And I take a map from the manifold to the two spheres. But you can think in dimension n if you want. So if you are very basic, what you will say is that the subset where the Jacobian of phi will vanish. So if you look at the set, if you want, sigma phi, okay, which is a set of x belonging, so this is my manifold M. X in M, okay, where the Jacobian of phi is equal to 0. If I look at this set, if you are if you are extremely naive, you would say that this is one equation, so it will give you an hypersurface in this. Okay, it will give you a codimension 1 subset. Okay, but this is ignoring complex geometry. This is ignoring the beauty of complex geometry. Because if the map was holomorphic, the Jacobian would be complex, okay, and its vanishing will give you two equations, not one equation. And that's a marvel, okay? That's a marvelous fact, okay? So in fact, you learn from the theory of complex manifold that you can always get such a map so that the place where the Jacobian vanishes is actually of codimension 2. So in fact, it's codimension equal to 2. Okay? And that's a fact which is not limited to dimension 2. It's true in general. Okay? And I will give you the construction. It's true in general that you can always find a map to the sphere in any dimension where the place where the Jacobian vanishes has codimension 2. Okay? Now, in the case of dimension 1, so there are a few points where it ramifies, okay, where the Jacobian vanishes. Too bad. For a single map, you cannot do it, of course, because the sphere is simply connected. You couldn't do it with a single map. Why can you do it with two maps? Well, I can take a little diffeomorphism here and move these points away from themselves. I will get another map, psi, okay, which will now ramify only on these other points. So the two sets where they ramify are disjoint. And because they preserve the orientation, the Jacobian is positive. So it will work, okay? It will belong to this set, okay? Okay. Okay, so it will belong to this set. Okay. Now, what is the geometric picture? The geometric picture is the following. It is this. Okay, and this geometric, so because you can ask me, but how do you get a map of very high degree now? Because we would like the volume of a Euclidean spacetime to be very large, okay, not to be Planck. How do you get to a very large volume? Well, you get it by triangulation. So, so this is illustrated by this picture. I took a torus, but I could have taken a Riemann surface much more complicated. You triangulate the, so this is due to Alexander. It works in any dimension, and I will explain the proof in any dimension of how you construct this map. So what do? You say that the sphere itself is obtained by gluing two simplices, okay? Two simplices together on their boundary. Okay, when you glue two simplices, but one of them I will call black, the other white. Okay. Now, why can I get a chessboard? Why can I get a chessboard triangulation like this, where the faces are alternatively black and white? How do you do that? Well, the proof of that is very simple. You first start with an arbitrary triangulation. But then you take what one calls a barycentric subdivision of this triangulation. And when you take this barycentric subdivision, what happens is that you can endow each of the vertices with an index, and this index is the size of the simplex that it contains. And so then what happens is that the vertices are indexed by 0, 1 up to the dimension. And then what you do, you color in black those simplices for which this order of the vertices coincides with the orientation, and in white those for which it doesn't coincide with the orientation. And you obtain a chessboard. Okay? So you obtain a chessboard. So it's possible to obtain a chessboard. There is no difficulties there. And what do you do then when you have this chessboard? What is your ramified cover? The ramified cover is that you transplant each of these simplices in an affine way on the corresponding white simplex in the sphere here, and you transplant each of the black one on the corresponding black one. Okay? And what you find out is that nothing happens on the common faces. It's all fine, because you go through. Okay? The only trouble which happens is at the vertices. So at the vertices you have ramification. Okay? At the vertices you cannot make it smooth, because there is ramification, all right, but not elsewhere. And Alexander wrote a paper in 1920, I think, or 25 or something like that, in which he showed how to do that in any dimension. You can do that for any manifold in any dimension. What you do, you triangulate the manifold, you take this refinement if you want, and then you take this map, and you find out that the map is ramified in codimension 2. Okay? So this is true in general. Okay? Now, why is it easy when the dimension is 2 and 3? Okay? Because you see, it ramifies in codimension 2, so this means that the singular set, so in general, if you want, this sigma phi has dimension equal to n minus 2. Okay? So this idea that you can move it by a little diffeomorphism of the source, okay, so as to make the sigma phi, if you add the sigma phi, if you want disjoint from sigma psi, then you are essentially in business, okay? And I mean, when you are, what does it mean to do that? Well, if you are in dimension n, here I have a subset of dimension n minus 2, I intersect it with a subset of dimension n minus 2. Okay, if n is equal to 3, okay, so let's take n equals 3, then n minus 2 is equal to 1. So here I have a subset of dimension 1, here I have a subset of dimension 1, okay, and by generic type argument, okay, it's easy to find that if you want the set of diffeomorphisms that will move it away from itself is a dense G delta in the bare category sense. So, I mean, you can find it, there is no problem. Okay, it's a countable intersection of open sets, dense open sets, so there is no problem. Okay, so in dimension 3 there is no problem. Yes, but now what about the interesting dimension, which is dimension 4? Okay, so if we take n equals 4, okay, then the problem is real. Why? Because it ramifies in dimension n minus 2, which is 2. Okay, so now the sigma phi is of dimension 2, the sigma psi is of dimension 2, but two subsets of dimension 2 in the 4 space, they intersect in general. Okay, There is no way. Okay, two subsets of dimension 2. I mean, you cannot take a subset of dimension 2 and move it away from itself by a diffeomorphism, of course. I mean, just think about, very simple examples. Okay, so we are in trouble. We are in trouble. And so there were a lot of discussions going on with geometers and so on. And then at first, okay, we were a little bit worried because there is a counterexample. So there is an example of a four-manifold in which you cannot do that. And I will explain the proof. This example was found by Sikorov and Sevenek, okay, in Lyon. I had contacted the people in Lyon, okay, they were working hard for several weeks, actually. For a long time, nothing was moving. I mean, but okay. And what is the reason? The reason is, in fact, very beautiful and simple. And what is the reason why you cannot do it for P2 of C? So if you take a two-dimensional projective space, it doesn't work. Okay. In fact, I had more or less come to the same conclusion for some other reason, because I was trying to take ramified cover of a force sphere using the fact that you can easily define the force sphere as a quotient of the two-dimensional complex projective space. But then you find out that it ramifies on P2 of R. And P2 of R turns out to be non-orientable. And this actually turns out to be the abstraction. Okay, and what is the proof why it cannot work for P2 of C? The proof is very simple. You see, imagine that you have these two maps which are mapping to the sphere, okay, and which are such that the intersection of the ramification point is empty. Well, what does it mean? It means that the manifold can be covered by two open sets, namely the places where the Jacobian don't vanish. So you have a covering by two open sets. And on these two open sets, the tangent bundle is trivialized. Why? Because the tangent bundle of the sphere is trivial when you add the line. So this means that when you pull it back, of course, by the Jacobian not vanishing, you will have the fact that the tangent space is trivialized on each of these open sets. But if the tangent space is trivialized on the covering by two open sets, it implies that the square of the second Stiefel-Whitney class, which is, if you want, the invariant of a real bundle. So the real bundles, they have Stiefel-Whitney classes. So what you find out is that the square, not the Stiefel-Whitney vanishes, but the square of the Stiefel-Whitney class actually vanishes. Okay, and this is not true for projective space. This is not true for P2 of C. Okay. Okay, but then, okay, we had a dream. And the dream was that, after all, in physics, of course, we are only interested in spin manifolds because we want the Dirac operator and so on. And the dream was that it should work for spin manifolds. And what is the condition to be a spin manifold? It's W2 equals 0. And of course, this implies that the square of W2 is 0. Okay? So that was a dream. And in fact, now it's a theorem. So it's a theorem. So our theorem is that, our theorem is that for any spin manifold, you can realize any volume, integral volume, which is larger or equal to 5. Okay, so this is our theorem. But now what is the idea? So as you will see, the proof will be much more interesting than this proof where I was moving away the singular set. I mean, this was too simple. So what is the idea now? The idea is quite beautiful. I mean, it came from a discussion with Donaldson. So it's so what is the idea now? The idea is totally different from this one. So we know that we can have, from Alexander, we know that we can have a ramified cover of the sphere. This is not the problem. So which ramifies in codimension 2. Okay. But now the idea, so if you want, now so I draw again a similar picture, if you want. I have this subset sigma phi where it ramifies, and I have the map to the fourth sphere. So now this is the fourth sphere, and this is a manifold of dimension 4. Okay, so this is M4. Okay, and it ramifies here in codimension 2. So sigma phi is a surface. Okay, it ramifies on sigma phi. What is the idea? The idea is a beautiful idea. Is that what do you have to do? You are not going to move away sigma phi from itself. I mean, this is not possible. you are going to take a small neighborhood of sigma phi. So I'm going to surround sigma phi by some neighborhood, W, let us say. Okay? And now I will do exactly as if I had a flat tire. I want to put a, I don't know if you call that in English. In French, we call it a rustine or something like that. So I want to repair what is going on near this, okay? But I want to repair it in such a way that I will not spoil what is going on outside. So how can we do that? How can we do that? Well, what we want to do is we want to get another map psi, okay? And this map will be a map from W to now R4, okay? Which will be smooth, and which will be an immersion. So with an immersion. So in other words, it will be such that the Jacobian of psi does not vanish. Does not vanish. Okay? Now, how on earth are you going to, first of all, to get such a thing? Okay, but imagine you have such a thing, which is defined near the singular set. Well, after all, you see psi is a map to R4. So as a smooth map to R4, it can be extended to all of M4. There is no difficulty there, because it's like extending each coordinate. So you can extend it. So you can extend the psi tilde, which will go from M4 to R4. Okay? Yes. So now I would like to use psi tilde and my original map phi. But I wouldn't like psi tilde to spoil the fact that the Jacobian of phi was not vanishing outside W. How can I do that? Well, I can make the Jacobian of psi tilde as small as I want by rescaling. You see? It will continue to be non-zero here, but it will be as small as I want on the complement. And so it will not disturb the fact that, that it doesn't vanish there. Okay? Okay, so this is the idea. But now, okay, now you have to find a psi. And this is the difficulty. Okay? So you have to find an immersion from this W to R4. Okay? Now there is a fantastic result, which is due to Smail and to Poenaru. And what is this fantastic result? It tells you the following. It tells you that if you take a manifold which is open, an open manifold of dimension n, and which is parallelizable, then it immerses in Rn with the same n. I mean, this is completely amazing. Okay, and this follows from the Smail theory of immersion theory as it's a theorem of Poenaru actually. Okay, so it tells you that what do you have to prove now? Now you have to prove that W is parallelizable. Okay, that the manifold W is parallelizable. But W is a neighborhood. It's like a neighborhood of a dimension 2 thing. Okay, this dimension 2 thing was the thing where you had the singular set for phi. Okay, and now we are going to make use of the fact that we have the spin manifold. The fact that we have the spin manifold tells us that we can lift the tangent bundle to the spin group. Okay, now the spin group. In dimension 4, what is it? It is SU2 cross SU2. Okay, SU2 cross SU2 has no topology below dimension 3. Okay, so but this neighborhood retracts on the space of dimension 2, so we are done. We know it's parallelizable, so we are done. Okay, so so this is what happens. This is what happens. And so it tells us that it's possible to repair the tire, okay? and to combine these two maps, okay? To combine these two maps so that the sum of the Jacobians will not vanish. It will not vanish, if you want, by positivity here. I mean, both of them preserve the orientation, so they are positive, if you want. So it will not vanish in the small neighborhood, and it will not vanish elsewhere, because we have a lower bound for the Jacobian of the original map phi, and we had to hit an epsilon. Okay? So this is the idea. This is the idea. And so what is amazing, if you want, is that the condition is exactly the spin condition. And so from that, we get the following corollary. So I don't know where the theorem is written in the slides, actually. I hope it's written somewhere. Let me see. Yes. So here is the theorem. So the theorem is the following. that if we take a smooth, connected, compact, oriented spin manifold, 4 manifold, then the invariant QM contains, so the possible values of the volume actually contains all integers which are bigger or equal to 5. Okay? In fact, by talking with Sullivan, I think 4 is also allowed. but you cannot get less than 4 because what you have to be able to reconstruct any topology by these covers. And of course, you know, I mean, it's not easy at all. Okay, so the mental picture which we get out of this is very much, if you want, the picture which I showed you before of the triangulation. So it's very much, this picture of the triangulation, I don't know, yes. So it's very much this picture of the triangulation. And now, if you want, what happens is that because we have two maps, you have to think of the following picture. You have to think that you have these two maps to a fourth sphere. The fourth sphere has a Planck size. So you have like an 8-dimensional space, which is the product of these two fourth spheres, which is of Planck size. Okay? And however, a huge space emerges as it was folded inside this product. You see, it was folded. But it unfolds, and the mental image is like the butterfly, which unfolds from the cocoon. Okay? But the point is that it can unfold to enormous dimensions. Okay? And there is a vague idea which we have not yet been able to put into use. And this vague idea is the following. You see, the sphere has beautiful properties that it has self-maps of I degree. Now, if you combine this covering with a self-map of the sphere with I degree, you do not change the volume by adding something. You change the volume by an e-folding, by multiplying by something. Okay? So we do hope that this operation, if you want, of multiplying the volume by some quantity has actually some physical content. I mean, this is what we are hoping for. Okay? But now, if you want, as a direct consequence of this process that we have, what we have is that now, if you want, we are no longer bothered by this enormous cosmological term that was in the spectral action, because when you expand the spectral action, the first term that you get is lambda to the 4 times the volume. Okay, and for a long time we were quite bothered by this term, because this meant that when you write down the variational equation, you don't. I mean, you get this cosmological term, which is like a preponderant term. But now that it is quantized, it's no longer the case. Because when you vary, you cannot vary something which is integral valued. Okay, so somehow what you will get then is really the Einstein equation coupled with matter. And this term will be there, you know, as somehow disappearing. Okay, so, and this is a picture. And there is an open question now, So there is an open question, which is that there is a Whitney embedding theorem. You see, the Whitney embedding theorem tells you that not only here you immerse, of course, I mean, the map to the product of the two force spheres is an immersion. Why it's an immersion? Because you know that one of the two Jacobians doesn't vanish. So of course it's an immersion. But you don't know that it's an embedding, actually. It's an open question whether you can fold it without self-crossing. Okay, I mean, that's really an open question. Okay, so now, however, I mean, we begin to get a picture for what we call an emerging geometry. And why is it so? Well, why is it so? Because now, if you want, from pure Hilbert space operators, you can see geometry appearing. And so what are the data? The data, they are of course the Clifford algebras, which you give once and for all because they have only one irreducible representation in Hilbert space. So you can give them once and for all. They are there, they don't move. They are like an extra structure in your Hilbert space. Same thing for the J. For the operator J, it's there and unique. Same thing for the chirality operator. They are all there once and for all. They are just decorations of the Hilbert space. The J is essentially telling you that this Hilbert space is quaternionic because J square is -1. So, I mean, it's really telling you that it's not an Hilbert space over C, it's an Hilbert space over the quaternions. Okay. So that's what you have. But then you have like a matrix model. And what is this matrix model? It's given by the Dirac operator, which is a self-adjoint operator, and by y plus y minus. But as I said before, it's better to think of y plus y minus as a single entity, which is the y, which is whose force power is equal to 1. So, I mean, essentially what you have is two matrices, D, which is self-adjoint, and Y, whose force power is equal to 1. And then there are some rules, which you can write down. Okay, there are some rules and so on. As I said, okay, there is this Whitney-Strong embedding theorem. And then what you do is out of this thing, you want to reconstruct the manifold. And it's metric. And this reconstruction of M is a very tricky thing. And I will discuss two aspects of it, which are extremely important. There are two aspects in it. You want to understand why is it true that even though the sphere was 8-dimensional, so you have 8 variables, because if you take the components of the y's, you have a total of 8 real variables. Why is it that you get something of dimension 4 out of 8 variables? I mean, this is something which which you have to understand, all right? And then, why is it true that the volume remains quantized? And when I write this quantity, if you want, you will see why. So, but this is a volume. I mean, this is it's really the volume of the space. So, sorry, the volume of the space. It shouldn't have been written this way. But I mean, it's really the integral of d to the minus n. I mean, this is what I should have written. This is the volume. This is the leading term in the. I should have written that. Okay. This is the leading term in the Weil expansion. Okay. So why is the joint spectrum of dimension 4? I mean. Okay, so this is here the dimension is taken as the Hausdorff dimension, and it comes from the growth of the eigenvalue of the operator D. So it's a fact that when the commutators, and they have to be bounded, okay, with the components are bounded, because when you raise them to the fourth power, you get something bounded. Okay, so the fact that these commutators are bounded together with the commutativity of the Y, this implies that when you take the joint spectrum of these operators, it's of dimension 4. It cannot grow more than dimension 4. Okay, that's a very, very delicate result on Hausdorff dimension, and the fact that the commutators are bounded. I mean, it's a kind of a control of the dimension by the growth of the eigenvalues of the operator, but in Fourier. Okay, so this is a general fact. Okay, then there is this question of why is the volume quantized? Okay, and why is the volume quantized? It's really a remarkable fact. I mean, it comes from the following idea. It comes from the fact that I can write this volume. So this is a volume by definition. Okay. What is this integral? This integral means the coefficient of the logarithmic divergence in the cutoff trace. Okay, which I explained in my first talk. Okay. So this is a general definition, completely operator theoretic of the volume. Okay, so the volume can be defined purely operator theoretic. Okay, why is this volume quantized? Well, it's quantized because you see the chirality operator satisfies gamma square equals 1. Okay, so now I can insert this one here. So this quantity is equal to integral of gamma times d to the minus n. Okay, but now I have a formula for gamma, because the Heisenberg higher order relation was an expression for gamma. Okay, it was expressing gamma up to constants as y, d commutator y. Okay, here it will be to the power 4 and the expectation value. Okay, so I replace this gamma by this value, and then okay, I get this expression, and now I claim this is an index formula in non-commutative geometry, that this expression here, in our case, will give us the index. Why is that true? This is very complicated. This is very complicated. It follows from the local index formula, but in order to apply the local index formula, one has to know that it's enough to know the Hochschild class of the cyclic cohomology Chern character of the operator D in order to compute this. In order to know that, you have to prove that the vanishing of the lower classes. So you have to prove that the idempotent, if you want, the K-theory class, which is corresponding to Y, has actually vanishing Chern classes of lower order. And this is the computation. And this is a computation which again uses gamma matrices. And it uses something which physicists know very well, which are called I think the Chern pattern factors or something like that. I mean, namely, it uses the fact that the Chern character is computed by computing the trace, but in a tensor product of matrix algebras. So then when you compute this trace, you find out that you get, if you want, the trace of the product of the matrices on the left-hand side. And these traces of products of matrices vanishes because it's exactly as before when I was saying that when I take the product of gamma matrices, it always vanishes except when you get exactly the right number of them. So what you find out when you do that is that the Chern character has all its components which vanish except the top one. And the top one is exactly what corresponds to the quantization condition, which is given by this formula here. I mean, I could replace the projection by the y here. It wouldn't make any difference because it's with commutators. Okay. So the theorem, if you want, is that if you take the algebra and you take these elements, then in fact all the lower components of the Chern character actually vanish. And as a corollary of that, when you look at the index formula, you don't have to worry about the lower components. You can only use the top component, and the top component I had computed in my local index formula in my book. I had computed to be given by this formula here, where this is a Dixmuir trace, namely the coefficient of the logarithmic divergency in the trace, and these are commutators. And when you apply it, you find exactly our quantization formula here. So you find that the volume is quantized. So if you want, this is in the direction of not making, I am not assuming that I have a manifold to start with. I am just assuming that I have an irreducible representation of these relations. And I am reconstructing the geometry. And, but moreover, the geometry has automatically a quantized volume. Okay, so this is the idea. So the idea is that out of operators, okay, that space-time in Euclidean form here appears out of operators in Hilbert space. And how do the points appear? They appear from the joint spectrum of these operators Y's. Okay? And how does the metric appear? The metric appears from the operator D, from the line element. So the hope, if you want, is that there is indeed a kind of matrix model which shows you how geometry emerges purely from the quantum, from purely quantum considerations. Okay. So I see that the time is really running. Okay. So let me just very, very, very briefly now go through what I had planned for the rest of the lecture. But I think I had planned for several more hours, actually, as you will see. Okay, so I'm a little bit sorry for that. But on the other hand, okay, I didn't want to rush, through this part because I really like it. I mean, okay. So the general theorem is that the quantization equation implies that the volume is quantized. So this quantity belongs to the integers. Okay, it's positive by construction. Okay. So there is another topic which I wanted to explain, which is that, as I said in my second lecture, one conclusion that we reached is that we had to take very seriously the model. And with Ali Shamseddin and Walter van Zijlkom, what we did is to take seriously this model where we have SU2 left, SU2 right, and so on. So in order to do that, we had to, you see, the reduction to the standard model is done by the first order condition. And we wanted to get rid of this first order condition. So this first order condition is really telling you that the Dirac operator is order 1 in the sense that when you take its commutator with an element, it commutes with the commutant of the algebra. Okay. Now, it was used in previous things because the action of the unitary group is by inner automorphisms, as it should be. Okay, so it's an adjoint action, if you want, in Hilbert space. So it uses both the left and right action. Okay, it uses the left action by U and the right action when you conjugate by J. And then when you write the gauge potentials, this gauge potential also corresponds to the adjoint action. So they have a J in it. And when you have the order 1 condition, things are very simple because if you want, these two things are independent. I mean, they don't interact. They commute and everything. So, with Walter and Ali, I mean, we were able to do this inner part of the metric without assuming the first order condition. And instead of going through the slides, which would be too complicated, I can tell you in a few words what we understood. What we understood is the following fact. We understood that exactly as, I explained to you that inside the group of automorphisms, you have inner automorphisms. Okay? But now let me explain to you what we found for the metric. So let me explain to you why you have an inner part to the metric in noncommutative geometry. Okay? The metric is given by the line element inverse, the D. Okay? So how is it that the D now can have inner fluctuations, exactly as there were inner automorphisms? Well, the simplest thing you can do for the operator D is to replace D by conjugating it by a unitary, U D U star. That corresponds to a trivial gauge transformations of the gauge potential. You don't change anything when you do that. You pass to an equivalent gauge potential. Okay? So this is just a gauge transformation on the gauge potential. So how is it now that you are going to get more interesting stuff? Okay? Well, it turns out that this is a group. This is a group of inner automorphisms. This is a group, okay, of inner automorphisms. But it turns out that there is a semi-group, which was hidden. I mean, I don't think anybody had found it before. So there is a semi-group which will give you all the gauge potentials for free. And what is this semi-group? This semi-group is you take, so now I will do the following transformations. I will replace my D by the finite sum of AI D times BI. And the only thing that I have to assume, okay, is that sigma of AI BI is equal to 1. Okay? Now, if you do that and you play with commutators and so on, you will easily find out that this is doing nothing else than adding to D, so you replace D by D plus a gauge potential, where the gauge potential is expressed as the sum of commutators, AI D commutator BI. Okay, this is because sigma of AI BI is equal to 1. Now, what is quite amazing is that these elements of this form, they form a semi-group. And the reason why they form a semi-group is something which had baffled us for a long time, which is that when you take an inner fluctuation of an inner fluctuation, it is still an inner fluctuation. There was no good explanation of that, except that there is a semi-group behind. Okay? And now this semi-group, you don't see it when you do ordinary differential geometry, because you only see its jet of order 1, because you only see the differential near the diagonal. Okay? But in general, I mean, it is there. Okay? And somehow, I mean, this is really the conceptual reason for the inner part of the metric. So once you understand that, when you develop it sufficiently well and so on, then all these things work out beautifully. And I mean, with Walter, and Ali, I mean, what we found, if you want, is that then this allows us. So we have this semi-group of inner fluctuations, okay, which is very nice and so on, and it allowed us to look at this model with SU2 left, SU2 right, and SU4 in general, okay, and what we did, I mean, is to compute the renormalization group running of the couplings and so on. When we look at this model, okay, so we looked at various cases. And there is one case which is extremely convincing, okay, where actually, okay, the couplings do meet when we do this extended model, this extended Paty-Salam model. So that was one thing which I wanted to explain, okay. But of course, I won't do it in detail. And so now time is running. Okay, and I just want to conclude with this. I just want to conclude with an idea, which I mentioned, I think, perhaps in the first talk or in the second talk. I don't remember exactly. But the idea is the following. Again, the idea is that the variability in the quantum is more primitive than the passing of time. Okay. Okay, we should be able to understand that. And why, if you want, somehow, if you want, I don't think we shall be able to come to terms with reduction of the wave packet issue unless we really understand at some point that trying to write everything in terms of an evolution in time is a wrong idea. That in the quantum there is a variability which is much more fundamental than the passing of time. And we have to rethink about it, and in particular, this will force us, you know, to see how time can emerge from the quantum variability. Okay, so I mean, the guy who is behind this is von Neumann, because von Neumann in the 1930s, 1940s, made very, very deep observations on subsystems of quantum systems. Namely, he tried to define formally, mathematically, what is a subsystem of a quantum system. And what he had in mind was that the Hilbert space of quantum mechanics would factorize as a tensor product. But since he was a very conceptual man, he didn't want to write that the Hilbert space factorizes the tensor product because the Hilbert space is not the quantum system. The quantum system is the algebra of observables. So he wanted to understand what this means for the algebra of observables, and he invented factorizations. And in his work with Murray, he found out that besides the obvious factorizations which come from factorization of Hilbert space, there were new factorization, type 2 and type 3. And what I found in my thesis, after the work of Tomita and Takazaki, I found that when you take a type 3 factorization, time emerges. It emerges from nowhere, namely that if you take a type 3 factorization, there is a canonical time evolution, modulo inner automorphisms, which doesn't depend on any choice. So that gave many, many invariants of the factors. It gave the periods, for instance, the times for which it doesn't move, and so on and so forth. But it did suggest an idea which has not been really used, and this idea is that, in fact, time should be something which emerges from the quantum. Okay? Namely that the origin of time, of the passing of time as we feel it, okay, is really the fact that the observables in quantum mechanics do not commute. Okay? And I think, I think we are really, really begging some really philosophical thinking about, for instance, what is quantum entanglement and all that. And that I don't think we take it in the right way. I think we are not taking it in the right way. I think we probably what it means. That's an idea which I already expressed, but I really want to insist on it. What it means is that, in fact, the alea of the quantum is like the clock, divine clock. So I mean, it is this which is setting up the passing of time, and entanglement means that the passing of time in these two places which are entangled is in fact synchronized. Okay, so it's not totally random. You know very well that if you have entangled states, okay, they are not independent. I mean, and I don't believe in this spooky action at a distance. I believe that actually there is some guy who is, beating the time, okay, but in a quantum way, and I believe that we are wrong in the sense that we are always trying to write a coherent past, but we are trying to write this coherent past in our own way, but I believe the quantum is much more interesting and much more, how to say, imaginative than our way of understanding it at the moment. Okay, so I think I will end here. Okay. Yes. Yes.
The time emerges from non-commutative in quantum, but we still have this Euclidean.
True, you are right. I mean, you see, I have to say one thing, which is that I have a few elements of an immense puzzle, and I cannot yet reconcile them at all. So, as you say, I mean, we were talking Euclidean before. Euclidean is mathematically much more easy because you don't have singularities for the propagator and all that. So it's mathematically much more easy. Now, the dream would be to reconcile these various pieces together, okay, and be able indeed, to understand, okay, a way in which geometry emerges, time emerges in a coherent manner. Okay, I mean, but I have no idea on that. I have no clue. No clue at all. I just have, as I said, a few hints. Yes.
Your concept heavily relies on quantum physics, right? On quantum theory.
Yeah.
And my question is, do you take quantum theory as it is today as a final version?
Well, that's a good question.
I
no.
remember of Einstein, he did not believe in quantum
theory. That's you see, my answer to this question is the following. I have been convinced, probably not of all details of the quantum theory, but at least of a few principles. The first one being the non-commutativity of the observables. Okay. The second one is the formalism found by von Neumann of Hilbert space. Now, the reason why I got convinced about it is not so much mathematical, but it's the fact that experimental physicists actually use it in such an incredibly fruitful manner. For instance, they understand concretely the two spheres. What I have in mind, if you want, is for instance, the talk of Sidney Coleman, where he was explaining quantum mechanics, and I mean, the title was Quantum Mechanics in Your Face. So what I am saying is the following. What I am saying is that one really has, the human mind is very adverse to these facts of quantum mechanics. I mean, they are not at all easy to understand except for the mathematical formalism. And I think, you know, we need, I don't know how many years of remodeling of the mind and so on, so that eventually we are able to think about it in the right way. But I don't think I am able. But at least, if you want, okay, I do not believe one word of anything that would say, okay, you know, the quantum doesn't exist, everything is classical and so on. This, okay, I mean, I'm sure this is the wrong idea. You see what I'm saying? So, okay, so it turns out, if you want, that, as I said, I mean, essentially the purpose of my lectures was to show how incredible insight Riemann had, where in 1853, I don't remember exactly, he was able to say something. Of course, there was no quantum mechanics at all, which eventually would be perfectly compatible with quantum mechanics. I find this absolutely mind-blowing. I mean, I must say, you know, that he was so careful, he was thinking so carefully that what he was saying was not wrong. It was not, you know, he was exactly sufficiently careful to say that in the infinity small, the metric relation should be governed by the forces and not by anything else. And I find this absolutely mind-blowing. Now, okay, we might be wrong. Sorry?
But what are the forces? I mean, if you replace the line element by the forces, and no one knows what forces are.
No, but But what I am saying is the following. What I am saying is that from purely mathematical reasons, you find that the line element should be exactly the inverse of this Dirac operator, which in it contains all the gauge potential, so it contains all the forces. I mean, and this is not, if you want, this is not deranged, this is not contradicted by what happens in quantum field theory, because you already have the gauge potentials there in the line element. This is exactly what I have in mind, you see. That's exactly.
You cover classical electrodynamics also from the line?
Yeah, of course, because it's a gauge potential, of course, you see, because it's a gauge potential. That's exactly what I am saying.
Yeah.
What I am saying is that the line element has in it the electromagnetism gauge potential, you see. So it has in it the strong force, it has in it the X field, you see, it has in it all these ingredients which will tell you what are the forces between the various things. It's not just the G news. It has all the ingredients which are needed. So in that sense, it might be considered as a realization of what Riemann had in mind. Of course, I mean, I know that, but I was very struck when I read again the Riemann paper to see that it was perfectly compatible with this. Now, I don't know if the formalism of quantum mechanics will survive. Okay, this is not clear. I can only quote what Sidney Coleman was saying at some point in his lecture. So he first explained the classical formalism of quantum mechanics, and after, it took him about 15 minutes, and then he said the following. He said, if anybody has a question at this point, please leave the room. Okay, I mean, that's a pretty arrogant way of putting it. Yes?
And as a technical question, how do you plan to address the operators? You talked yesterday that you are planning to...
Yeah, there is a difficulty there. There is a big difficulty, which is gauge fixing. You see, because you have gauge fields, okay, and so the difficulty there is to be able to do the gauge fixing in the right way, to dress the line element. For electrodynamics, there wouldn't be any problem. But when you look at for instance, the strong force and all that, this would be more complicated. So this is an open question, of course. But of course, I mean, for electrodynamics, you don't have any problem.
But I mean, analogy of Schmidt-Dyson equation and everything?
Well, no, I think the right question there is different. The right question is really a physics question. Namely, one would have to find a physics experiment of measurement of distances in the very small, where this dressing would appear. So you see, one would have to find an experiment where you are measuring distances using this Dirac propagator. I don't know if the electronic microscope would do it or something like that, because you have to have something where the measuring is not done, of course, by an arc, where you measure the ds of the arc, but where you measure it by sending photons, for instance, okay? Or by sending electrons. That would be actually better. And if you send electrons, then this Dirac propagator should enter in the computation of distances. And if you are in a situation which is sufficiently fine, the dressing should enter. Yes?
If you have a charged particle, does it move along the geodesic of the metric?
What do you mean? The metric is non-commutative, so you would have to say what you mean by geodesic. But
The shortest line.
yeah, but it moves according to an equation which is an operator equation. Okay, and geodesics are replaced, as I said, by exponential IT absolute of d times the vector. Okay, so this is what is the geodesic in this sense. But I think this is the right question. The right question would be to find a physical experiment of measuring small distances where the dressing could enter into play.
So the plan is to input in the theory already dressed operators?
Sure. I mean, if you want, okay, it's obvious that if we would understand the quantum theory, at the moment there is no h-bar, okay? If we would understand the quantum theory, of course the geometry would be different. The geometry will be dressed, and it will be of course much more, elaborate than that. But the principal part, if you want, we have. The dressing we don't have, okay, of course, because we don't have the quantum theory. But it's quite believable that one could imagine a physics experiment with charged particles, with electrons, for instance, okay, in which the measurement of distances would actually involve the dressed propagator, not the bare propagator, not the original one. I think this is a very interesting question. It's really a physics question. I am not a physicist, so I cannot answer. But I don't know exactly the mechanism of the electron microscope. I mean, I don't know how it works. I mean, I don't know how these things work. So.
Okay, so is there